Hello and welcome to our next lecture. Today we're talking about so-called quarter period series. The reason they're called quarter period series is because contrary to the series we considered before, which had function sine and cosine going through multiples of half periods over the interval 0 to L, this time the sines and cosines will go through an odd multiple of a quarter of a period on the interval 0 to L. So just as before, we're going to consider two separate bases, one that's comprised only of cosines, one that's comprised only of sines. So for quarter period series, and I'm using quarter period in quotation marks because it's not an official name for the series. I'm using quarter period just to emphasize the fact that the function's going through multiples of quarters of the periods on the interval 0 to L. The basis functions will be for the cosine series, let's call them phi k. It's going to be cosine of 2k plus 1 pi t over 2l. And for the sine series, let's call them psi k. It's going to be sine 2k plus 1 pi t over 2l. K will be going from 0 to infinity. So before we start considering the coefficients, I have to show that I have orthogonal bases. So I will have to check the inner product of cosine with every other cosine, and we'll have to check the inner product of every sine with every other sine. I'm not going to check the inner products between sines and cosines because these are two separate bases. Before, for the real Fourier series, I had to consider the inner products between sines and cosines because they were members of the same basis. This time I have two different bases, so I don't have to cross-check them for their orthogonality. So let's verify that we have two orthogonal bases. So I have to check the inner product of every phi k with every phi j. And I will have to check the inner product of every psi k with every psi j. And also to make sure that I have a basis, I have to make sure that every cosine has a non-zero norm and every sine has a non-zero norm. So we'll have to compute the norm squared of phi k and the norm squared of every psi k. I'm going to do that in Mathematica just because it's a lot easier to do it this way. So I already typed up everything. First I'm going to check if every cosine is orthogonal to every other cosine. Notice here I just divided everything by 2, so it's instead of 2k plus 1 over 2, I will have just k plus 1 half. So let me compute this inner product. This is what I'm going to see. It's very obvious from just looking at this formula is going to give me 0, because if j and k are different, then j minus k is going to be an integer, and sine of any integer of pi is going to be 0. The same goes for the second sine. It's just going to be 0 because what is inside a sine is an integer multiple of pi. But just to make sure, I'm going to ask Mathematica to do all the work for me. And sure enough, Mathematica tells me that this inner product is actually going to be 0. Let me compute the inner product of every sine with every other sine. So it's the same kind of a formula, except that cosines are replaced with sines. Computing it gives me exactly the same expression. Well, this is not surprising because what we're going to see later, that the cosines and the sines of quarter periods are actually reflections of each other, so their integrals have to be the same. And just to check that their norm squared are not 0, let me compute the norm square for the sine and simplify it. And it simplifies into L over 2. If I do the same for the cosine, I get exactly the same integral, which simplifies again into L over 2. That's to show you what I mean by the quarter period series. I have this little demonstration. So here I have graphs of the functions. The first is the graph of the cosine, the second is the graph of sine. And I'm going to increase k and see what happens. So here I have just 1/4 of a period of each function. Jumping k by 1, I see that what I'm adding is a half of the period for each function. So it's just 3/4 of the period of cosine and 3/4 of the period of sine. Increasing k again, I can see that I have 1 1/4 period for each one of the functions. And you can see how that increases by periods by a half. So I always have an odd multiple of quarter periods for each one of those functions. So let's write it all down. So these inner products are always going to be 0 if k is not equal to j. And the norms squared are always L over 2. Therefore, if I have a function from L2 from 0 to L, I can express f of t as a summation, k goes from 0 to infinity, of ak times the cosines where ak is 1 over norm squared, which is 2 over L, the integral from 0 to L of the function f of t times the cosine. Or I can express the function f of t as a summation. As k goes from 0 to infinity of bk times the sine of 2k plus 1 pi t over 2l, where bk are computed as 1 over the norm squared. Again, it's going to be 2 over L, the integral from 0 to L, f of t times the sine of 2k plus 1 pi t over L dt. Again, let's use two of my favorite functions. So here I want to use the same 10th function and the same piecewise constant function, shift it into the interval 0 to 2, and I want to compute the quarter period series for each one of them. I'm going to use Mathematica to compute all of the series because the coefficients are quite long and the integration is quite long, so it's a lot faster to use Mathematica. Here I have my f of t defined. I will compute the coefficients ak as the integration with the cosine. And if I try to compute a few coefficients, I get some non-zero numbers for each coefficient. So let's add a few terms together and see how this approximates my function. Let's overlay it with the function just to see how well this represents it. We see the representation is not that good, but if I start adding more terms, you can see that it's getting better and better with the addition of each term. I want to point out one property of the cosine series. It's always going to 0 at the right endpoint because every function in the cosine series goes to 0 at the right endpoint. And it has a 0 derivative at the left endpoint. And on the opposite side I have sine, which is always 0 at the left endpoint and always have a 0 derivative at the right endpoint. Take a look at some other basis functions and you see the same thing happen. I have a 0 derivative for the cosine at the left endpoint and 0 at the right endpoint. And for the sine I have 0 at the left endpoint and 0 derivative at the right endpoint. So this series will always try to maintain it. You will have a 0 derivative at one endpoint and 0 at another opposite endpoint. So here adding a lot of terms results in the approximation that almost coincides with the actual function. So I'm going to delete it now and see what happens with just the approximation. So you can see the approximation still has a 0 derivative at the left hand point. That's something the cosines will never give up. And the property is important in certain cases of solutions of partial differential equations. So let's look at the sine series. How does the sine series do? So I'm going to compute the coefficients p, k, and compute an approximation with a few terms. And again, let's overlay the function f of t just to see how close this approximation is to the function it tries to approximate. Not very good, but again, if I start adding terms, I'll get convergence. And just as before, I have my series, my approximation, always being 0 at the left end point and having a 0 derivative at the right end point this time. So let me erase f of t and plot just the approximation. And just out of curiosity, let's look what happens outside of the interval, how these functions behave outside of the interval 0 to 2. You see, both of them are trying to make some weird periodic extensions of the functions. So the function tries to reflect itself around the y-axis and then tries to flip itself over the x-axis at the same time. Since these are quarter period functions on the interval 0 to L, each one of the basis functions will be periodic on the interval from 0 to 4L. And we can see here that these functions are periodic on the interval from 0 to 8. But they are slightly different versions of the periodic extensions of my function. But that's understood because one of them tries to do it with cosines, another one tries to do it with sines. But both of them are trying to extend the function in a certain way and then flip it around and repeat itself and then flip it around and repeat itself. Makes them periodic on the interval from 0 to 4L. So let's look what happens to the function g. There's a familiar function g. The formula for the coefficients is quite complicated. If I compute a few of them, then I can recognize the pattern in them. As you can see, the -1 starts to change the sign, and the negative square root of 2 becomes positive square root of 2, and then I have odd numbers in the denominators. If I wanted to, I could express this as a pattern, but I don't think it's worth our time to do that. So let's go ahead and compute a few approximations and plot them on the interval from 0 to 2. So how does that correspond to the function we're trying to approximate? Well, this is the function we're trying to approximate. The approximation is not very good, but as I start adding terms, I can see how it starts becoming better, better, and better. If I add a lot of terms, you can see how my approximation tries to converge to the function. With a large number of terms included in the summation, I see the Gibbs phenomenon now returning. And here's an interesting thing. With the cosines, the left hand point should have a 0 derivative and the right hand point should jump to 0. And as you can see, because my cosine series doesn't try to jump to 0, there's no Gibbs phenomenon on the left hand point. But there is a Gibbs phenomenon on the right. And if I try to plot it on a larger interval, you can see why, because the cosine series tries to first reflect around the y-axis as a first repetition and then only rotated by 180 degrees. So let me delete the function just to see better what's going on with my approximation. It's kind of hard to see, but this periodic extension is periodic on the interval from 0 to 8, and that's expected. Let's see how the sine series behaves. I'm going to compute the coefficients pk. I'm going to compute a few approximations. Let's put the function g of t together. So what we see, put in a few more terms, gets us closer. Now we can see that I have a Gibbs phenomenon on the left end and no Gibbs phenomenon on the right end. And that's just because the sine quarter period series has a zero derivative at the right end and jumps to zero on the left end. Plotting this on a larger interval, we can see how this function is again periodic from 0 to 8. At the point 8 it jumps exactly to where it was right here and then goes down, up, repeats itself this way, etc., etc. So we can see that both sine and cosine quarter period series serve as an independent basis. And as I mentioned before, these different types of series arise when we start solving partial differential equations, and different boundary conditions force the solution to be expressed as series expansions with one of those series. And just as before, I want to look at the function t e to the minus t on the interval, this time 0 to 3, and see how both sine and cosine series fare in approximation of this function. Cosine series will want the expansion or approximation to have a zero derivative at the left end and jump to zero at the right end. And it seems like this function is ill-suited for this type of approximation. And we're going to see what kind of problems this will create. So the formula for computing the coefficient is 2 over L, this times 2 over B, cosine of 2k plus 1 pi t over 2b. Here again I canceled 2 in the 2k plus 1 and 2l on the bottom. Integration evaluated from 0 to b. The coefficient looks quite complicated, and if I start plugging in numbers it doesn't make it any better. But for mathematics it doesn't make any difference. Let's try to plot this function with one approximation. Well, it doesn't look very good. Let's put h of t together. It's not a good approximation. Adding a few more terms will make it better. Still not very good. That's a lot better. Put a lot more terms, and the graphs are almost indistinguishable except for the Gibbs phenomenon on the right. So let me delete function h of t from the plot, and you can see that the Gibbs phenomenon propagated itself almost to the middle of the function. And if I plot just a few terms, you can see that the zero derivative on the left is maintained, and it prevents the function from reaching zero. So it's not a very good approximation of the function at either one of the ends, and also not a very good approximation of a derivative of the function if we want to compute the derivatives. The derivative of the approximation will oscillate wildly, while nothing like that happens for the actual function. So let's see what the sine series does for the same function. Again, let's plot a few terms. Let's put in function h of t. That's not a very good approximation, but as you can see, the sine does a lot better job in approximating this function, because sine naturally tries to start from 0, where this function actually starts, and having a non-zero derivative at the other end is not really a big problem, because the derivative is actually not very far from 0. So for the first 15 terms, we'll already see a much better result. It approximates the function very well. And by deleting the function, I can see that maintaining zero derivative at the other end will always happen for the sine approximation. But it doesn't create those awful ripples that the previous approximation did. Unfortunately, there is no way to predict which approximation will have the Gibbs phenomena prevalent and which approximation will fare a lot better in terms of the Gibbs phenomenon. And also, when we solve the partial differential equations, the type of the series that we have to use is forced upon us by the boundary conditions, so it's not like we can choose which series to use. But we see nonetheless that both sines and cosines are quite capable to represent functions from L2, and they're quite capable to serve as a basis if you're willing to use half-period or quarter-period expansions. So the main takeaway from all those series discussions is that we have several different types of series. We have a complex series, a real series uses both sines and cosines in a single basis, half period series that use only sine or cosine, and we also have this quarter period series, also use either sine or cosine. I hope you're not getting overwhelmed with all those different types of series. Once you get the idea where they're coming from the perspective of inner products and orthogonality and how the formulas are actually obtained, you will see that all these series have a lot in common. So I hope you enjoyed the discussion today, and I'll see you in our next video.